Okay, good morning, everyone.
Morning.
Good morning. Today we're gonna talk about one last piece from section 2.8, which is coordinate with respect to a basis, and then we're gonna move on to determinant and talk a bit about determinant. So coordinate with respect to a basis, and you very quickly, what is it about? Suppose I am in R2, the universe, so its coordinate, let me write down the title, coordinate with respect to a basis. So we're going to talk about coordinate with respect to a basis. So before I state the definition, let me tell you very briefly what is it about. Suppose I am in R2. So I'm taking all the vectors that has two components. And take the regular vector, the unit vector that you are very familiar with, the E1 and E2. Those two vectors, they form a basis for R2. So remember, a basis for R2 are vectors that are linearly independent. And when you take their span, you get all of R2. So those are form a basis. And we grew up, all of us, mathematically at least, knowing the following, that if you have any point here, any point, let's say 2, 3, then 2, 3, we can write it as we've done several times, 2E1 plus 3E2. And we call 2, 3 the coordinate of this point. That's what we call them, the coordinate of this point. It means 2, 3 tells me that this point here, to get to this point, basically, you need to go 2 this way and 3 this way. And we used those coordinates basically to describe the position of any point in the plane. So if I want to tell you what this point is, I basically tell you what are the coordinates. I tell you what the point is. I want to tell you what this point is, I tell you what the coordinate of this point, and then you know exactly which point I am talking about. Now the idea here is today is the following. If I take any two vectors in R2, almost any two vectors, suppose any two vectors. So let me call those V1 and V2. So V1 and V2. Any two vectors, as long as they are linearly independent. So if I take any two vectors, V1, V2, which are linearly independent. Now, if I am in R2, so that's my universe, I am in R2, those vectors form a basis. So we're gonna call B to be V1, V2, and those form a basis for R2 because they are linearly independent. That's what the picture tells you. And when you span them, you get all of R2. So R2 is the span of those two vectors. So what does this mean? R2 is the span. It means any vector in R2 can be written as their linear combination. And we've seen this geometrically very much so. So if I'm going to pick this vector here, an arbitrary vector, I can write this as a combination of V1 and V2. And the way we did it really since day one in this course, we said, okay, we're going to think of those as two different directions. And how can I get from here to here following V1 and V2? And according to my picture, that did it in a very, basically. So this was like almost like that. Almost like that. So this vector X, I actually wrote it as follows. As V1 plus V2. So X, I wrote it as V1 plus V2. It means I need to go 1 unit in this direction and 1 unit in this direction to get to X. And I can express any vector I want, anything I want as a combination of those two. It means I can tell you, if I pick any point, I can tell you how to reach it following V1 and V2. We are gonna call those weight 1 and 1 the coordinate of the vector X with respect to the basis V1, V2. So we're going to call those weight the coordinate of the vector x with respect to the bases v1 and v2. So intuitively, the idea is the following. All our mathematical life, we express the coordinate of a point with respect to E1 and E2. So if I tell you 2, 3, means I'm telling you where's the position of 2, 3 with respect to E1 and E2. And now the idea is I don't have to use the E1 and E2 to express the position of a vector. I can tell you where a vector is by telling you its coordinate with respect to V1 and V2. It means by giving you the weight I need to get x, but the weight with respect to V1 and V2. So, and we're gonna call the coordinate of x with respect to the basis B, we're gonna write this in my particular example, 1, 1. And this is the idea of changing the coordinate system. It means instead of using the x1, x2 as a coordinate system, I can use those two lines basically as my new coordinate system. Intuitively, I can use V1 and V2 as my new coordinate system. And instead of expressing everything in terms of E1 and E2, we're going to be expressing them in terms of V1 and V2. And this is an idea it's basically very much used as the idea of changing coordinate. So we don't use the regular, we use a new coordinate system, and we express every vector in terms of the new coordinate system. So that's the idea of a coordinate with respect to a basis. So I have R2, I create a basis for it, and then I express everything in terms of this new basis. The weight will be called the coordinate of x with respect to the basis B. So that's really the idea of the coordinate with respect to a basis. Now I'll just give you the formal definition and I will have a simple example. So what's the coordinate with respect to a basis? So suppose H is a subspace of Rn. Again, as I always said, for us to grasp, to think of subspaces, at least we can think of the subspace of R3. Line through the origin, plane through the origin, all of R3. So we can have kind of a picture in our mind. All of R2, that's a subspace. And let B be a basis for H. Let us remember, what does it mean? It means that they are linearly independent and every vector in H is the linear combination of those V1. So that's what a basis is. They have to be linearly independent and everything in H is obtained from them. So let X be a vector. Then in H is in here. Then I can write as a combination of the V1 and V2. Then the coordinate of X with respect to the basis B are the weight, C1, C2 through CK, such that X can be written as the C1, V1 plus C2, V2 plus CK, VK. So in other words, if you take a vector in H, you can write as a combination of V1 and V2 and VK. The weight, C1, C2, and CK, will be called the coordinate of the vector X with respect to the basis B. And how do we write this? We write X bracket B. The coordinate of X is C1 through CK. Those are the weight. And this is read the coordinate of X relative to the basis. And the entries of the coordinate depends on the order in which we write the basis. So the order here is going to affect the coordinate, which is also true when I write E1, E2. So when I write 2, 3, 2 is the coordinate with respect to E1, and 3 is the coordinate with respect to E2. With respect to any basis, the way I'm going to write those will actually depend on the order, I give the basis B. So that's really the idea of a basis coordinate with respect to a new basis. It's really the idea of changing the coordinate system. Instead of using our regular one, but I'm telling you, you can scratch the regular one, take any two vectors, suppose I'm talking in R2, take any two linearly independent in R2 and use them as a basis for your coordinate system and express everything in terms of that. So two very simple examples to elaborate this idea. So suppose I take the following vector. All right, 1, 2, minus 1, 1. In this order. They form a basis for R2. So let's try to understand first this notation. So I'm telling you that X is a vector. Its coordinate with respect to this basis is 5, 6. Okay? What does this mean to you? What does it mean to write X bracket B equal 5, 6? And I'm asking you to find X. Which vector really I am talking about? So algebraically, what is X? It means that 5 and 6 are the weight that I should put on V1 and V2 to get the vector X. So this means that the vector X is actually 5 times the first basis plus 6 times the second basis vector. So I'm telling you, if you want to get the vector X, you have to go 5 units in this direction, and you have to go 6 units in this direction. So I'm giving you how to get to a vector, but not using the regular coordinate system, by using V1 and V2 as my new coordinate system. So that's what this notation means. Question number 2 is, I'm going to give you a vector. So I tell you, let X be the vector 1, 5. And my question to you is, find the coordinate of X with respect to the basis B. So I'm going to first answer the question algebraically and then geometrically. So what am I asking about in this problem? Okay, I have to do the geometry. I cannot work without geometry. So what am I asking you about? So I have this basis. I give you any vector, and I tell you find the coordinate of X with respect to the basis. What am I asking about? Can anybody speak up?
It's saying find the linear combination of the two basis vectors to reach X.
Right, exactly. It means I want to find the weight I have to put on my vector V1, V2. Sorry, that's nonsense. It means I need to find the weight C1, C2 that I should put on V1 and V2 to reach my vector X. So I'm going to find C1, C2 such that X is the linear combination of those two vectors. So I'm giving you a particular vector. I'm asking you. So here the coordinates are with respect to E1 and E2. This is the regular old coordinate. Find the coordinate of X with respect to a basis. It means how much weight I should put on V1, how much weight I should put on V2, exactly to reach the vector X. So algebraically, it's actually now it's a fairly simple problem. We just set up the system. I'm going to set up the system 1, 5. Sorry, if you don't see that screen, I don't see because I don't pay attention sometimes myself. Okay, so we're going to solve the following system. 1, 2, that's the base, minus 1, 1. And go after the weight. So we do all the math we usually do. And I did that on the sheet. I'm going to get 0, 3, 1, 1, minus 1, 1. So I'm getting that. So what does this mean? It means that, sorry, I got 3, 3 here. It means that C2 is 1. That's what this one would read. And C1 is 1 plus C2. It means C1 is going to be equal to 2. So this means that my vector X is 2V1 plus V2. It means that the coordinate of X with respect to this basis is actually 2, 1. So if I want to tell you what my vector X is, I have two choices. I either tell you X is 1, 5. Here I'm giving you the coordinate with respect to E1 and E2. Or I can tell you, okay, the coordinate of X with respect to the basis B is 2, 1. It means I tell you this is you go 2 in direction of V1, 1 in direction of V2. This is the total idea of changing the coordinate system. Changing the coordinate system. And now geometrically, what I am doing is actually here. This is my V1, which is the vector 1, 2. And this is my V2, which is the vector minus 1, 1. And this is X, which is the vector 1, 5. And what I'm really actually doing is what the picture tells you. I want to get from here to here following V1 and V2. So I need 2 in this direction and 1 in that direction. So this 2 is act like E1 and E2, exactly like E1 and E2, but they are different vectors. And 1 right there. So the coordinates are 2 and 1. Okay. And why do we use that? Because sometimes, a lot of times actually, it's easier to work with a new coordinate system than with the old coordinate system. For some object, so if like, let us say, as a simple example, suppose you have an ellipse. I will not dwell a lot on it. Now, if this ellipse have those as major axes, the equation of the ellipse will be x squared plus y squared equal to 1, a very simple equation. Now, suppose my ellipse doesn't look like that. My ellipse looks something like this. That's my ellipse. Now, in this scenario, the equation, if I use the regular coordinate system, the equation of the ellipse is actually fairly complicated. However, if I use for coordinate system, the major axis and the minor axis of my ellipse, if I try to express every point here, the coordinate relationship between every point on the ellipse. So if I take a point on the ellipse and I think of its coordinate with respect to this basis, the equation of this ellipse would become very easy. So the equation will become very easy as long as I take a point and I call big X and big Y the coordinate of this point with respect to those two vectors, then the equation of the ellipse will be like the equation of the ellipse as if it were centered, having major and minor axes on the X and Y axis. So sometimes the picture forces us to actually express the equation in terms of a new coordinate system, not the regular coordinate system. So that's really the idea, which is used tremendously. Sometimes you see a picture and say, you know, it's hard to express in this way, but it's easier if I look at the different coordinate system. So one more example, and then we proceed to determinate. My second example is here. Let me take H to be the span of 1, 1, 0, 3, 4, 2. So my H here is the span of two vectors in R3. So I'm taking two vectors and I am spanning them. And that's my H. It means my H is nothing more than a plane in R3 because that's really what two vectors give me. And the basis for H are 1, 1, 0, and 3, 4, 2. They form a basis. They are linearly independent. And H is nothing more than their span. So now I am in R3, but my subspace is not all of R3. My subspace is basically those two vectors in R3. And now, so it's slightly different than the previous example because H is not R3, H is a subspace in R3. And now I'm giving you the following problem, is the following question. You're giving that the coordinate of X with respect to B is 1, 4. What is X? So as you realize now, the coordinate has two components. It's not three components. Because in my case, my H is the span of two vectors. So if I'm telling you the coordinate of X is 1, 4, it means I'm talking about the coordinate of X with respect to the basis that we just gave you. So what is X? What does it mean? So here I'm telling you X is a vector in H, and its coordinate is 1, 4. Means that to get to the vector X, I need to go 1 unit in this direction and 4 units in the direction of the vector 3, 4, 2. So this tells me two things. It tells me that my vector is in H, and my vectors, how can I get to it? 1 unit in this direction plus 4 units in that direction. So what are the coordinates of x with respect to the basis? Question 2 is, suppose I take a vector in R3. I want you to show that x is in H and find its coordinate with respect to the basis B. Okay, now what is H? H is the plane. H is the span of those two vectors. Okay, that's my H. Show that X is in H. It means we have to show that X is a combination of those two vectors. Find the coordinate of X with respect to H. It means that since it's a combination of those two vectors, the coordinate will be the weight of those obtained by writing X as a combination. So X is in H means X is in the span. So to show X is in H, we can solve the system X equals C1 times this plus C2. So we solve the system. We solve it and we realize, so we put 1, 1, 0, 3, 4, 2, 5, 6, 2. We solve and we realize that the vector C2 is 1, C1 is 2, which means that the vector X is a vector in H because it's in their span. And to get to it, I need to go 2 in this direction and 1 unit in that direction. So we say that the coordinate of X with respect to this basis is 2 and 1. So the only confusing idea here is that my X has 3 components. But the coordinate of X with respect to the basis consists of 2. And the reason here is that my subspace H in this case is nothing more than a plane. So that's here what the picture is. This is my vector V1, this is my vector V2. The span is this plane. And now I'm taking a vector in the plane. And I am asking you to write it as a combination of those two. So that's the idea. We call this the idea of coordinatizing the plane. It means coordinatizing the plane. It means we are taking the plane within R3 and we create a coordinate system within the plane. And we express everything in the plane as a linear combination of those two vectors. So it's the idea that you have a plane in R3, you're only interested in this plane, you're not interested in anything else. So you create a coordinate system. So you pick two vectors linearly independent within this plane, and you express everything in terms of those two vectors. So the reason we have two coordinates, it's because I am working within a plane in R3. I'm not working all over R3. I'm creating a coordinate system right in R3. And that's we call this coordinatizing the plane, creating a coordinate system within the plane. Now I can do also that in R3. It means instead of working, I will not give you examples because the examples become, the algebra is fairly simple, but the idea is actually more important in those problems. So in R3 also, we are used to use E1, E2, E3 as a basis. And the question is, again, you don't have to use those as a way to express the coordinate of every vector in R3. As long as I take 3 vectors, that they are linearly independent, I can express anything. I can use those 3 vectors as a coordinate system and express everything in terms of this new coordinate system. And that's one of the use, of course, in linear algebra, because a lot of pictures lend themselves into a new coordinate system and not instead of the old coordinate system. Okay, any questions before we move on to an absolutely kind of new idea? Any questions? All right. So today we're going to start section 3.1, which is determinant. Now I know that all of you have heard the word determinant, but now we're going to start defining it in a more, of course, the right way. So determinant. Suppose A is a 2 by 2 matrix. All right, so A is the matrix ABCD. What's the determinant of A? The determinant of A, that we write it by determinant of A, is given by, you take the matrix ABCD, And when we write determinant, instead of surrounding the entries by bracket, we surround them by two straight vertical lines. And for 2 by 2 matrix, the definition is simple. The determinant is AD minus BC. So for a 2 by 2, the definition of determinant is AD minus BC. But now we're going to stretch this idea for 3 by 3, 4 by 4, 5 by 5, and so on and so forth. And that's become our first definition of the determinant. So let A be a n by n matrix. Let Aij be the matrix obtained from A by removing the ith row and the jth column. So we start with A, we remove the ith row and the jth column. So the remaining matrix is going to be n minus 1 by n minus 1 matrix. We're going to call this Aij. So it's matrix obtained from A by removing ith row and jth column. So now back to definition of the determinant. Suppose A is n by n matrix. N by n, the notion of determinant is only defined for an n by n. It means a square matrix. So I don't talk about the determinant of a 2 by 3 matrix. We talk about determinant of 3 by 3, 4 by 4, 5 by 5, and so on and so forth. So suppose A is the following. We're going to define the matrix determinant as follows. It's equal to. Okay, I'm going to put those together. All right, here we are. I think. So it's going to be equal to A11 times the determinant obtained by removing the first row and the first column minus A12 times the determinant of the matrix obtained by removing first row, second column plus A13, the entry here, times the determinant obtained by removing the row where the A13 is and the column where A13 is, etc., etc. The sign alternate, and finally I reach the last term, and the sign in front of it will be either plus or minus depending on n. And say again, this entry times the determinant of the matrix obtained by removing the row where this entry is and the column where this entry is. So that's the definition of the determinant. So we're going to take that and start practicing exactly how to compute the determinant. So instead of reading the note, I will work it out with you. So it's become easier for us. So I'm going to take the following matrix and word by word, I'm going to compute it. So let me take the following matrix. 1, 3, 1, 0, 1, 2, 2, 4, 1. And we're going to use the definition to compute the determinant. So determinant tells me, definition tells me, you take A11 times the determinant of A11. So let us understand what does A11 mean. A11 is the matrix obtained from A by removing first row, first column. First row, first column. So A11 is 1, 4, 2, 1. That's A11. First row, first column. Now what is A12? A12, we remove first row, second column. That's what those Aij are about. And finally, what is A13? We remove first row, third column. First row, third column, we get that. So now, what is the determinant? So the determinant of A, I follow the definition verbatim. It's the first entry. Sorry. The determinant of A is A11. It means this entry here. Times the determinant of A11. It means determinant of the matrix obtained by removing those. So 1, 4, 2, 1. Minus A12, 3, this entry, times the determinant of the matrix obtained by removing this row and this column. 2, 1. Plus, so the signs alternate. This entry here, which is 1, times the determinant of the matrix obtained by removing the row where this entry is and the column. So which leave me with 0, 2, 1. So to find the determinant of a 3 by 3 matrix, we actually have to find determinant of 2 by 2 matrices and 3 of them. Now the rest is we just compute. 2 by 2, I just gave you the definition. It's 1 minus 2 times 4 minus 3 times 0 minus 4 plus 1 times 0 minus 2. And now I do the math, I will get minus 7 plus 12 minus 2, which is going to give me 3. So the determinant of my matrix is equal to 3. Now, as if we have 4 by 4 matrix. If we have a 4 by 4 matrix, nothing changed. The definition is the definition, and it's just tedious, but it's the definition. So let us do it a little bit for a 4 by 4 matrix. So here I'm putting a comments in my notes. When we write a matrix, we put brackets around the entries. When we talk about determinant, we put vertical lines around the entries. So we have to be very careful in the way we write them. A matrix is just a rectangular array of numbers. The determinant is one number. The determinant is a number. It's not a matrix, it's just a number. Now, what if we have a 4 by 4 matrix? Okay, so a 4 by 4 matrix. How do we compute the determinant? And it's verbatim the same. It's just more work and just a bit more messy. So let us do the setup for the determinant of a 4 by 4 matrix. So what's going to be? Okay, so I will write it here. Okay, so what's the determinant of this matrix? It's the first term, which is a 4, times the determinant of the matrix obtained, removing the first row and the first column. So I will be left with 1, 0, 2, 3, 1, 4, 1, 2, 1. Minus the sign alternate. This entry, 0, times the determinant. Now I know 0 times anything is 0, but just to get the picture clear, of the matrix obtained by removing the row where 0 is and the column. 0, 0, 1, 3, 1, 4, 1, 2, 1. Plus signs alternate. The entry 2 times the mess here, 0, 0, 1, 1, 0, 2, 1, 2, 1. Minus 0 times the last one that I will not write. So finding the determinant of a 4 by 4 requires 4 determinant of 3 by 3. So this is really how it gets a little bit messy. Now I have to compute each one of them. This is exactly the one I gave in the previous example. So this is nothing more than 3. This is a 0 plus. This is a 3 by 3. So I need to compute it. I have to open my parentheses and actually compute it. I'm going to get 0. As you realize, I put a lot of 0 because to avoid a lot of mistake. Minus 1 times 0, 1, 2, 1. Plus 1 times the row here, I get 0, 0, 1, 2, minus 0. Now I compute this whole thing. I compute, this is a 12. I compute this new determinant and I get 60. So finding a 4 by 4, the determinant of 4 by 4 matrix is not hard, it's just tedious. So we have to compute 3 by 3. For 3 by 3, we have to compute 2 by 2 and so on and so forth. And that's the reason why MATLAB is in existence, because it's tedious work, not hard work, but we should definitely know how to do it. So that's how we find the determinant. Part 2 is the following. There are other ways that we can compute the determinant. And let me describe in a few words what's really the idea. The definition I gave here tells you that you take, you take this terms, A11, means you look at the first row and you compute A11 times determinant of A11 minus A12 and so on. So you use the first row to be able to compute determinant. The theorem that we're gonna really talk about now is telling you don't have necessarily to work with the first row. You can work with the second row. There is only a problem with the sign, how the sign alternates. So if you work with the second row, it's gonna be basically minus, plus, minus, plus. So the sign alternate in a different way, but the idea is the same. So instead of using this row to determine, I can use that row or the following row and so on. I can use also columns to compute the determinant. The only things will change in the picture are how signs will alternate. And that's what the second idea is going to be about. And you will tell me why this is a very useful idea in a second. But before that, let me introduce how it works. So equivalent way to find the determinant, and we call this cofactor expansion. So first, what does the word cofactor mean? Suppose A is an n by n matrix. Then the ij cofactor of A is a number, and it's the following number. So the ij cofactor of A is the number, it's written Cij, which is the determinant of Aij times a certain minus 1 to the power I plus j. So it's basically plus or minus the determinant of Aij, depending on I and j. Before we state the equivalent way, let us a little bit study the Cij. What are those? So, okay. So I state the theorem and then I will basically work with it. So let A be n by n matrix. Another way to find the determinant is, as I said a minute ago, we can use any column or any row. So the first piece tells me the following. Suppose A is an n by n matrix. Then I can use any row. So suppose I use the ith row to compute determinant. This tells me that the determinant is AI1. AI1 means the first is the term in the ith row and first column. Times, instead of the determinant of AI1, it's going to be the cofactor Ci1 plus. So I'm focusing on one row. The second term of the row will be ith row second column, Ci2 plus ith row third column, Ci3, and so on and so forth. This is called cofactor expansion across the ith row. And the theorem tells me you can work with columns. It means you can, instead of focusing on a row, you can focus on a column. It means I can do that. So this is my j's column. So the term is going to be A1j, A2j, ANJ. And it's going to tell me the following. You can take this term times this cofactor that I'm going to talk about in a second, plus this term times this cofactor, etc., plus that term times the cofactor. And we call this cofactor expansion down the j's column. So how to use the theorem? So this theorem is involving this new thing that I called cofactors. But what are those cofactors? So let us note something. The Cij cofactor is minus 1 to the I plus j times the determinant of Aij. Now, minus 1 to the I plus j is either a plus or a minus the determinant of Aij, because depending on the I and j. So this is Cij that I'm talking about is basically the determinant of Aij, but there is a plus or minus sign. And the plus or minus will depend on the position of Aij in the matrix. So let me analyze a little bit those Cij, and working with them will be very easy, as you will see in a minute. So for example, what's C11? C11 is minus 1 to the 1 plus 1, the determinant of A11. It means it's plus the determinant of A11. So if in the formula we see C11, this is going to be plus the determinant of A11. So I'm going to put a plus sign here. This plus sign here tells me that the -1 to the 1 plus 1 is positive. It means C11 is plus the determinant. Now what's C21? It means C21, I am here. It's -1 to the 2 plus 1 determinant of A21. It means the C21 is minus the determinant of A21. Now C31, if I compute, it's going to be plus the determinant of A31. Now if I take every cofactor and I try to find whether there is a plus or a minus here, what's going to happen is if C11 is going to be plus, C21 is going to be minus, sorry, C12 is going to be minus, C13 is going to be positive determinant. So we're going to call this here, this is called the checkerboard sign. And the entries represent the sign of -1 to the I plus j. So it looks probably very confusing to you right now, but the practice part is fairly simple. So I'm going to immediately start practicing this idea, and you will realize that it's not really as hard as it looks. So suppose I'm going to take the following matrix, 1, 3, 1, and I'm going to compute this matrix, not like I did it a minute ago, but I'm going to compute this matrix using the idea of cofactor expansion. So I will do that slowly, and then the rest will be simple for you. 1, 3, 1, 0, 1, 2, 2, 4, 1. And my question is, I want you to find the determinant using cofactor. Let me pick the third row across the third row. So we're going to compute the determinant by doing cofactor across the third row. And let's see how it works. So the determinant of A is this entry. That's what it tells me. The entry. But instead of having the determinant of this piece, the theorem tells me you have to multiply this by something they call the cofactor. So, and this is the cofactor, and this is the third row, first column. It's going to be that. Plus 4 times the cofactor of that term is third row, second column, plus 1 times the cofactor of this. This row is third row and third column. That's what it tells me. Now, this is equal to what? The 2 is a 2. Now, C31. Is this positive, the determinant? So that's the determinant of A31 times a certain sign. Is this sign positive or negative? That's the question that changed from before. Now, to determine whether this sign is positive or negative, basically that's what I'm going to use the checkerboard sign. And what does this tell me? The checkerboard sign tells me that if you're looking for C11, this is going to be positive here. This C21 is going to be negative to determinant. C31 going to be positive to determinant. So instead of computing, so this should be -1 to the power 3 plus 1. But instead of having to really work with it, you ask yourself, okay, the checkerboard sign tells me -1 to the 3 plus 1. Is it going to be positive or negative? It's going to be positive. So this is going to be +1. Now what's C321? So checkerboard sign is going to tell me that this is going to be minus the determinant of A31. So instead of a plus, this is going to be minus the determinant of A32. Actually, -1 to the power 3 plus 2, 3 plus 2 is 5, it's going to be -1. Now the 3 plus 3. Okay, is it plus the determinant of A33 or minus? The checkerboard sign tells me for 3 plus 3 is going to be the plus. So plus the determinant of A33. So now we can do this. It's going to give me 2 times that's a positive. A31 is the determinant obtained by removing the term in that contains this, the row that contains 2, and the column that contains 2. So I'm left with 3, 1, 1, 2 minus 4 times the row and the column that contain 4 has to be removed. So I'll be left with 1, 0, 1, 2 plus A33, I'll be left with 1, 0, 3, 1. So the sign here alternate, of course, but sometimes they will start with a minus and then minus, plus, or they start with a plus, minus, plus, minus. In this scenario, they started with a plus. Now I'm going to give you another scenario where they start with a minus. So now we compute all this, and we should get honest to goodness 3 like previous problem. All right, I will do one problem along those lines, actually, and then we have to say why we're bothering with all this, because of course there should be a reason, otherwise you won't be bothered with it. So now my last example in this particular problem, I'm going to take the same matrix, I will not even change it, and I want to compute, but I'm going to pick something else to compute the determinant. So this is 1, 0, 2, 3, 1, 4, 1, 2, 1. And I'm going to compute the determinant by doing cofactor down. Let me pick a column this time. Let me do it down the third column. No, down the second column. Okay, so down second column. Okay, and that's what we're going to do. All right, so how does it work down the second column? And this time I'm going to be a little bit faster than before. So determinant of A equal. Okay, I'm going to use this column. The first thing I'm going to do is actually draw here a little bit my checkerboard sign on the side. Minus, plus, minus. So this minus here tells me that when I'm going to take the cofactor, the cofactor is going to be minus the determinant of the matrix obtained by removing the row and the column that contain 3. So the way I'm going to start is, instead of really writing the whole formula, I'm going to say, okay, the cofactor here is going to be negative the determinant. So I'm going to start by writing minus 3 times the determinant of the matrix obtained by removing the row and the column that contain 3. 0, 2, 2, 1. And then I'm going to keep going. If this is minus, then this is going to be a plus times the determinant obtained by removing those, which give me was 1, 2, 1, 1. And finally, minus 4 times the determinant obtained by removing the row and the column that contain 4, which give me 1, 0, 1, 2. And now I just have to compute those. That's it, 2 by 2. We know how to do that. 2 by 2 we know, and 2 by 2 we know. And we compute this, we get a 3. So that's really how we use the cofactor expansion. We pick a row or pick a column, and then we do determinant by using this particular row. So why is this useful? Can anybody tell me why this is useful? Why having the luxury of picking a row and a column of our choice is actually useful?
You could pick a row or column with the most zeros.
You can pick the row and the column with those zeros. As simple as that. So suppose I give you this series. Sorry. This matrix. 1, 3, 1, 1. 1, 1. Or 1, 10 for that matter. I don't care. 0, 1. 2, 3. Actually, I don't even want a 0 because I have no intention of computing that. 5. And then I give 2, 4, 1, 2. And then I give you that. And I tell you compute the determinant. Okay? If I use the original definition, It means I will have 3 by 3 determinant to compute, because I have to do 1 times this minus 3 times the rest plus 1 minus 10. So the idea is we don't have to do that. We can choose this row to do the determinant because it has a bunch of zeros. The only thing I have to worry about is make sure I get the size of the cofactors, not the sign, the plus or minus part of the cofactor straight. Minus, plus. So it means the determinant of A, as you realize, I have to put it immediately between vertical line, is going to be 1, because this is 0, 0, 0, times the determinant of what's left over, the determinant of that, which is 1, 5, 2, 3, 1, 4, 1, 2. So now, instead of doing lots of determinant, I can do one of them because we have a bunch of zeros in here. So I can choose this row to compute the determinant. So that's really the benefit of this cofactor expansion. And of course, that's a lot of benefit because we can play those kind of games. All right. Now, determinant is useful, but as far as linear algebra is concerned, the most important idea for us is going to be that the determinant are going to allow us to decide whether the matrix is invertible or not. So that's really the main reason we study determinant in linear algebra. They're going to give us a tool to tell us whether the matrix is invertible or not. And that's exactly toward that tool that we're going to start heading. So my goal now is to use the idea of determinant to get to the main thing I want in this from determinant, which is to show that a matrix is invertible if and only if its determinant is different from 0. So we're going to build this connection between a number, the determinant is a number, and the invertibility of a matrix. And this is one, actually, that's the most important reason we study determinant in linear algebra. Of course, it has other application, but that's what we care about in this course. So now I'm slowly going to head that route. Now we know how to find it. And we're going to head toward the idea of invertibility. But before that, we need a lot of preparation for that. So the first thing I going to talk about is the determinant of very, very specific, special type of matrices. So determinant of special type of matrices. First, diagonal matrix. Those are very easy matrices. So diagonal matrices are matrices of the following form, diagonal. It means they have terms along their diagonal and zeros everywhere else. This is diagonal matrix. So a typical diagonal matrix is 1, 4, 5, 0, 0, 0, 0, 0. This is a diagonal matrix. Now, what's the determinant of a diagonal matrix? It means that's a matrix. What is its determinant? All right, let's find a formula. And the way we're going to find all those formula is basically by doing it for 2 by 2 and so on. So what's the determinant of that matrix? D1, D2 minus 0. Okay? What if I take 3 by 3? What's the determinant of this matrix? Quickly.
D1, D2, D3.
Yeah, why? Just use the first row. D1 times the determinant of that matrix. What's the determinant of that matrix? D1, D2, D3. I can do that for 4 by 4, 5 by 5, 6 by 5. So for a diagonal matrix, the determinant is the product of the term along the diagonal. So for a diagonal matrix, the determinant is the product of the term along the diagonal. All right. The other special type of matrices is what we're going to call the upper triangular matrix. Upper triangular matrix. Now, what's an upper triangular matrix? Is a matrix where all the terms above the all the terms above the diagonal are non-zero. In other words, an upper triangular is the matrix where all the terms below the diagonal are zeros. All the terms below the diagonal are zero. So what's an upper triangular matrix? So those are n by n matrix. So this is D1, D2, D3, sorry, Dn. All the terms below are zero. And those could be anything you want. That's an upper triangular matrix. What does this matrix remind you of? Does it remind you anything we've seen? Which matrices have that form? Come on, remember.
Echelon form.
Exactly, speak up.
Echelon form.
Echelon form, exactly. Those are how the echelon forms usually look like. They are zero below the diagonal and a bunch of stuff above the diagonal. What's the determinant of this matrix? So I want to start, we're going to start analyzing what's the determinant of this matrix. And the only way I know how to do it, is by, building it up. If it is 2 by 2, it's 3 by 3. All right, help me out. What's the determinant of this one? Okay, that's easy. D1, D2 minus 0. What's the determinant of this matrix? I give you a minute to figure it out.
D1, D2 times D3.
Do you agree with him? How did you do it?
The same way as the previous one, because that's 0 multiplied by whatever number that is, it's still going to be 0. So
You
you
did
just look at
cofactor expansion
yeah,
along
the first column.
first column. So we're going to do cofactor down the first column. So we do cofactor down the first column. So that's a plus, and then you have so many zeros. So that's a very good way to do it. So cofactor first column is going to give me D1 times D2, 0, star, D3. All right, we're going to get D1, D2, and D3, which is interesting. Regardless what stuff I have here, that did not affect the value of the determinant. The determinant remain the product along the diagonal, even though I can have any kind of numbers up here. So in general, now this is the rule. If you have an upper triangular matrix, again, so D1, star, 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 D2, etc. Dn, those could be anything, but those could be 0. The determinant is also the product of the terms along the diagonal. Okay, so those are special matrices, and that's really what the determinant are. Now, another special matrix, the same way you have upper triangular, you can talk about a lower triangular matrix. And a lower triangular matrix is a matrix where all the terms above the diagonal are zeros. So a lower triangular matrix, it means you have a bunch of terms along the diagonal. And here you can have anything you want, and everything here is going to be 0. That's a lower triangle. Everything above the diagonal is 0, and below we can have anything. Again, we can show that the determinant is the product of the terms along the diagonal. So specific matrices, diagonal matrix, they have easy determinant, and upper triangular also have very easy determinant. It's just really the product. Other matrices, no, they don't. The determinant is actually a bit more involved. Yeah. But this is interesting here. So if a matrix is in echelon form, say n by n, computing its determinant is fairly, very simple. Now we know that every matrix can be somehow reduced to a form like that. Am I right? It can be reduced by performing row operation. So now we're gonna see the following. When you take a matrix and you perform a row operation on it, how will this affect its determinant? Since the echelon form itself have very easy determinant, what we're gonna see is what's the effect of row operation on the determinant of a matrix. All right, so that's gonna be our next job. What are the row operations? Let us remember them. The row operations are switching rows, scaling a row, multiplying a row by replacing a row by the sum of itself and a constant multiple of another. These are the three elementary row operations that we worked with throughout the whole semester. And now my question is, what's the effect of each one of them by itself on the determinant? All right, so let us a little bit explore those together. So suppose I have, and we'll only do it for a 2 by 2 matrix, and then I will state the rule. So effect of elementary row operation on the matrix. Right. Suppose I have a matrix A, B, C, D, only 2 by 2. The general approach is a little bit hard. And I switch rows. So A, B. So from here to here, the operation I did was exchanging the rows. Only that, one operation. So what do you think is the effect on the determinant if we do that? Just compute the determinant in your head, actually.
Just flips the sign.
Flip the sign, because what's this? AD minus BC. Now what's that? Basically BC minus AD. So when you switch rows, you actually flip the sum. And if we think a little bit about the cofactor expansion, we realize that that's actually what's happened. The sign, if you use this row versus that row to do cofactor, and it's the sign that's actually play a role. So the first effect is that, I read it. Suppose a matrix B is obtained from a matrix A by exchanging 2 rows or 2 columns. It doesn't really matter. Everything I'm going to say about rows work for column. Then the determinant of B is minus the determinant of A. So switching column really multiply the matrix by a negative. But what if the second row operation we did was multiplying, scaling a row. It means multiplying a row or a column by a constant. So suppose I do this operation. I have a matrix A, B, C, D. And I multiply a row. So this is going to be my new matrix, obtained from the first by multiplying a row, 1 row, not 2 rows, only one by a constant. How will this affect the determinant? So the determinant of this one is AD minus BC. I take a row, I multiply it by K. What's going to happen to the determinant of this new matrix? All right, because that's an easy scenario, I'm going to really do it. So it's going to be, this one is KAD minus KBC. I can factor my K. I will get AD minus BC. So if I multiply 1 row by a constant, the determinant will change. But what's the relationship? The determinant of the new matrix is just K times the determinant of the old matrix. So that's the effect of scaling. So again, we're gonna read it right there. Suppose B, a matrix B, is obtained from A by multiplying 1 row, not 2, not 3, 1, by a constant K. So then the determinant of B is K times the determinant of A. So I also have the picture to be very clear. Suppose that's my original matrix, and this is my B. That's the B I'm talking about. So this is the matrix obtained from this one, multiplying one row by a constant. I have a whole new matrix. The determinant of this new matrix is K times the determinant of the old matrix. So I can basically factor out the K as long as I multiply one row by a constant. Now, the last operation, which is by far the most important operation we performed, because that's what actually got me to the echelon form. So what is the last operation we performed? What we call replacement operation. And this operation was the following. Suppose I have a matrix A. So this is my matrix A, B, C, D. And let us remember what was the most important operation. The most important operation is replacing a row by the sum of itself and a constant multiple of another. That's really the most important operation. So suppose here I replace R2 by the sum of itself, that's the operation, plus a constant times R1. That's the operation I'm doing. I'm going to replace this one by the sum of itself and a constant multiple. So this will give me the following matrix. A, B, and I'm replacing R2 by the sum. That's going to give me C plus KA, and this is going to give me D, the sum of itself, plus KB. That's the operation I did. And the question is, what's the relationship between that and that? Because we know that that's the operation we perform the most. And interestingly enough, they will have the same determinants. So performing this operation will not affect the determinant. The proof is not trivial in general, but for 2 by 2 actually is easy. It means if I take this matrix, the determinant is AD minus BC. If I take this matrix, the determinant is A times D plus KB minus B times C plus KA. And if I do the math, I get AD plus KAB minus BC minus KAB. This and this simplify. I end up with AD minus BC, which is exactly the same. The proof in general is not very hard, but it's definitely more complicated. But the main thing is this picture here. I have a matrix A. If I replace a row by the sum of itself, this one should not change, and a constant multiple of another, I'm creating a new matrix. This new one will have the same determinant as the original one. And this is going to be the most useful fact, basically, that I'm going to use. So I'll write it right here. Suppose a matrix B is obtained from A by replacing one row of A by the sum of itself and a constant multiple of another. Then the determinant of B is equal to determinant of A. And that's the picture. It means you have any matrix A and you do the following. You replace the second row, for example, by the sum of itself plus a constant multiple. Then you don't change the value of your determinant. So this is how the row operation affects the determinant of this matrix. Okay. Next time, we're going to use this idea to show you why the determinant tell us whether the matrix is invertible or not. Today, I just want to practice a little bit this idea here for the last few minutes. We're going to just practice this. So I'm going to take any matrix. Do I have any? I should not waste papers. Here I am. Suppose I'm going to take the following matrix A A, B, C, D, E, F, G, H, I. So that's an arbitrary matrix. And I'm going to tell you this is a matrix A. And I'm going to tell you that the determinant of this matrix is, I don't know, like a 7. All right, that's the info I gave you. And I'm going to ask you to find the determinant of other matrices that are obtained from A. So we start with the following matrix. So let me take this A, B, C, 5D. So I'm going to multiply a row and G, H, I. What's the determinant of this new matrix? It's very clear what I did. And what's the determinant of this new matrix based on what we did before? Quickly, everybody, 35. Because what did I do? I multiplied one row by 5. So this is going to give me 5 times the determinant of A. It means 5 times 7. All right? Okay. Suppose I do the following. A, B, C, and what do you think this will be? What's the determinant of this new matrix?
Would it be 105?
Based on, I don't know. What did you do?
I just multiplied 5, 3, and 7.
Right. Is he correct? Is it 5 times 3 times 7?
I think so.
You think so? Let's do it. Okay, we're going to do it slowly. The first step is I'm going to factor out this 5. And this is going to give me A, B, C, D, E, F, 3, 3, 3. Is this correct? Yes or no? What do you think?
Yeah.
Yeah, because what did I do? I only focused on this row. And I took the 5 out. I kept this in touch. I did not really touch it. I can't because there are 2 row operations. Now the second piece would be I'm going to pull out this 3. 5 times 3 times that. And now I get exactly 5 times 3 times 7. You guys told me 105. I trust you. No, I don't think so though. Yeah, 15 times 7. Okay. Now, question number 2. Suppose I take the following matrix. So 2 more examples. This one is again simple. A, B, C, D, E, F, G plus 3A, H plus 3B, I plus 3C. 3, 3, 3. What's the determinant of that matrix?
7.
That's 7. This hasn't changed. Now, sorry. If you guys want to work it out, one way to work it out, you say this is equal to the following. 7, absolutely correct. This does not really change at all. But one way you can actually see it, so you say, okay, I'm going to go from here to here by the following operation. So I'm going to replace, and that is a reason I'm doing this. So from here to here, I say, okay, I'm going to replace R3 by the sum of itself minus 3 times R1. This operation does not change. So I replace R3 by the sum of itself minus 3R1. Basically, I'm cutting rid of the effect of the 3A's. So what do I get? A, B, C, D, E, F. I'm going to replace this one by the sum of itself minus this. Means minus 3A plus 3A. So I'm going to get G, H, I. This operation does not change, it's going to be equal to 7. My last question is the following. Okay, so I'm gonna keep this in front of me. This is not gonna go, but I'm gonna give you now the following matrix. And that would be my last example. D, E, F. And this is gonna give me, let me see what I'm gonna do. 2G plus 3A, 2H plus 3E, and my last one is going to be 2I plus 3C. What's the determinant of this new matrix? I want all of you to think about it, all of you. Is that very clear? Okay. Somebody, Alex is telling me 14 with a question mark.
I don't think it's 14, just because if it was 14, it would be 14 if it was plus 6A plus 3E and plus 3C. Or sorry, 6 and 6. That.
So what do you think is the answer? Mikey tells me 14.
Two.
Actually, no, I changed what I said earlier. I do think it's 14.
It's absolutely 14, and let me get you to 14 in a very, 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 that's why I did this piece here, very systematically, so we will have no doubt about it. So my first operation is going to be, I want to get rid of the 3A, sorry, that's 3B. What am I writing? I'm going to get rid of the 3B, and I'm going to get rid of 3C. I can do that because I'm going to perform first this following operation. I'm going to replace R3. It has to be replaced, and that's a bit tricky. That's the only operation. By the sum of itself, it means I'm going to replace it by, I'm not going to touch this, by the sum of itself minus constant multiple of the first row. So the idea is that I'm going to take this, I cannot touch this, but I can add something to it. This I cannot touch, but I can add constant multiple of another. This doesn't change the operation. But by doing this, what do I get? A, B, C, D, E, F. What do I get by doing this? I'm multiplying this by minus 3A and then adding it. Minus 3A plus 3A, this is going to give me the 2G. And this is going to give me the 2H. And that's going to give me the 2I. I have 2, 2, 2. Now I can factor out my 2, and I get A, B, C, D, E, F, G, H, I. And now I'm getting 2 times 7, which is 14. Okay? Because here, actually, I did not do one row operation between this matrix, my original matrix A, and this. There is not only one row operation, actually 2 row operations were being performed. We actually did replacement, we multiplied this by 2 and we did replacement. So we have 2 row operation. And the theorem I told you, tell us if you do 1 row, what happens when you do 1 row operation. So it works one by one. When you do 2 row operation, you cannot use the theorem. You have to break it up into 2 operations to be able to use the theorem we did. And now that's what I did here. I broke it up into 2. First, I got rid of 3A, 3B, 3C. This one did not affect the determinant, but then I have the 2's and the 2's and the 2's. This did affect the determinant, and it's going to give me 14. Okay, so we define determinant today. The definition is simple. You definitely have to go over it, learn how to compute determinant, important. And then we saw, well, how do they affect the elementary, how they are affected by the elementary row operation. And next time we're gonna see that basically, what does this have to do with the invertibility of a matrix? Why studying determinant really tell us when a matrix is invertible. And actually, I give you a guideline how your calculator compute determinant, which is definitely not by using the formula I gave you, because it's very messy, too hard to compute, actually by using what I just talked about, the idea of row operation, which make it much, much simpler. Okay, so for next Thursday, of course, you have your regular quiz. It's going to be about the coordinate with respect to a basis and determinant that we talked about. And as far as your exam, I haven't looked at it yet. It's going to be a little bit before I grade it. So be patient. Okay, any questions before we leave the section? Okay, good luck, guys. Bye. I'll see you on Thursday.